right, so today we're actually going to start looking at imaging physics. We're going to start out with echocardiography. And recall, echocardiography was this imaging technique where you have a transducer in your hand. The echotech has the transducer in their hand, and they shoot a beam of sound into the patient, and they look at reflections of sound, and that creates images of the heart. So you have to point the sound between the ribs or underneath the rib cage. You can put the transducer down here as well. So I've put a couple of websites up here. I wanted to be agnostic in terms of company, but GE Health, Philips, Siemens, and there's Toshiba, a lot of other ultrasound companies. And to look at state-of-the-art pictures of ultrasound, these are the best places to go. These sites where the companies show their latest and greatest stuff. I might have this up already. Let's see. Yeah, so on this website you can just go through and see examples of some of the images that can be obtained. And so here's an example. This is a pretty simple example. The EKG is down here, so it looks like this data is over 2 heartbeats according to this EKG here. And here the transducer, the ultrasound transducer, is up at the top of this picture. Oh, I'm sorry, hit the wrong damn thing. No, that's not going to work. Okay, so it's up at the top here. It's shooting sound into the patient through their chest wall, which is right here, and their heart is just under their ribs. And as you can see, it looks sort of like an edge image. There is little signal inside the cardiac chamber itself, but there's a lot of signal off edges, like this valve here. The heart wall itself shows a bright signal. Can you tell me, or let's look at, say, spatial resolution of these images. Obviously, it's a sequence of images played back in time. As we move away from the transducer, you take a look at the detail that you can see here versus the detail you can see down here. There's a pretty obvious depth dependence on image quality in this modality. Obviously, we can make images fairly quickly because each image, we're playing these back at, I don't know, 15, 30 frames a second or something, and we're seeing a movie, right? And the great thing about echocardiography is this is done in real time, right? So you have the transducer in your hand, and the pictures coming up on the screen are what's happening right in front of you. So it's a pretty remarkable technique that way. It's a two-dimensional technique in the sense that you have this 2D field here, and obviously there's some kind of depth associated with each signal in this picture, and we'll take a look at how you calculate or how you figure out how thick that depth is. Any other questions about these images? You can make these pictures while you're asking the patient to do things like, ride a bicycle, or you give them drugs to stress the heart and see how the heart reacts and things like that. So it's a really powerful imaging technique. So we will jump out of here. So I would encourage you, if you go back, let's close this. You can just take a look at all of these fantastic examples of echo, and on this, and the Siemens site has examples. Here's looking at volume over time. Here's some quantitative function over time. It's great stuff. Okay. So get out of there, and there's a couple other websites here as well. So how does it work primarily? Here's the picture on the right, and the transducer is on the left here. You can see it's a fairly small object, it's quite light. The transducer has on the front of it an array of ceramic crystals that vibrate at a very high frequency. We're up in the megahertz, and that's what creates the sound waves. This transducer sends out a beam of sound waves, and it has a certain thickness, which we'll call a slice thickness, or the elevation. It has, if we make a pixel in this field of view in front of the transducer, you have lateral resolution, which is the angle resolution, which is the resolution in this direction in the picture. And then axial resolution is the resolution in this direction. So how sharp is an edge when I draw a profile down through here? How sharp is that edge? You can see it's pretty sharp that way. This resolution depends heavily on depth. As you can see, as we go down, it gets blurred in that direction, in the lateral direction. So the basic principle by which these signals are created are their longitudinal or compression waves of sound. Okay, and so if I put a transducer element, which is sort of in this cartoon is represented by this surface right here. This is my transducer element, and I push it back and forth in this direction when it is sitting up against a material, which is this spring right here. So this is the body. This is our transducer that's sitting on the chest wall. Usually you have a coupling gel to make sure that there's a really nice coupling here. And you move this thing back and forth really fast. So at megahertz, 20 megahertz oscillations. And that creates pressure waves that move through the material. Right? So you press the particles together, and then they come apart, and they push together, and they come apart, and they push together. And so that longitudinal wave, a sound wave, travels with a specific frequency and has a specific wavelength, right, which is the distance between two peaks in the pressure. Okay? And the shape of that wave as it's moving through the material depends a lot on the compressibility of the material, or this sonic impedance of the material. So something that's highly compressible, like air, it turns out the sound moves more slowly, the wave moves more slowly through the medium, versus water, in which the sound travels faster. And so essentially what we're going to use is this physical phenomenon to do echolocation. And we'll use the echolocation to create the picture of interfaces in our object. And so do people understand the principle of echolocation? Bats use it they chirp, and then with their ears they listen for the time delay between a wall and so they know the distance to the wall, they don't hit it. Has anybody, as a kid, did you measure the distance to a fireworks display by measuring the time delay of the sound to get to you? Did anyone do that? Raise your hand if you did that as a kid. No? Oh. Your parents should have taught you how to do this. So you watch the fireworks, and you're, say, 4 miles away, and they're at SeaWorld, and you're on your balcony at home or whatever. Fireworks goes up and goes in the sky, right? So you see a big flash when the thing bursts, and then you hear it 3.5 seconds later, right? Nobody's done this. It's amazing. It happens all the time. It happens every 4th of July. You just look, and it's like, and then, boom, there's the sound, right? So now you've got 2 data points. You have precisely the start of that sound wave when it's traveling towards you, because that's the flash of light, and then you have the sound when it hits you. And so you just count up 1,000, 2,000, 3,000, boom, and then you measure that delay. And you know the speed of sound in air, so you can calculate the distance to the object, right? So it's a really fairly precise way of measuring distance in the 5-mile range, right? Something like that. If it's too close, like if it's 100 meters, it's really loud for one thing, right? So anyway, that's echolocation. In that case, instead of knowing exactly when we push the sound out and listen for an echo. That was our, an echolocation, that's your start time. What we know is, because the light travels essentially instantly, you know the time of the start of the sound at the source. Right? So basically, just like any wave phenomenon, the speed of the sound in a medium, the frequency of the oscillating wave, of this pressure wave, times the wavelength gives you the speed of the sound in the medium. And the speed changes in different media, okay, because of its compressibility. Very non-compressible things will have very fast sound waves. So if I have a steel beam and I compress and I give an impulse of sound by taking a hammer and going bang and hitting it on one side of the steel beam, the compression wave through that steel beam is going to be very fast, and I'll hear that sound on the other side. If I put a little microphone or transducer there, it'll go, come through really quickly, right? If it's air, on the other hand, it'll take time to get there. So the speed in a medium is given by basically the compressibility. This thing B, it's called the bulk modulus over the density, right? So here's for us, for ultrasound physics, in terms of we're imaging people, right? We just need to know the speeds of sound in parts of people, right? So there's highly dense stuff in people, right, like bone, right, in which the speed of sound is 4,000 meters per second, 4 kilometers per second. And then in muscle, like soft tissue all gathered together as muscle, the speed of sound is about 1,500 meters per second. Right? So that's kind of the speed of sound in water, 1,480, 1,500 meters per second. Does anybody listen to whales in water? If you go underwater, I've never heard them here, but in Maui, in April, when the whales are all passing by, they're all migrating, you go under the water, you can just hear hundreds of whales tick, 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 talking to each other. So that basically is going at 1,500 meters per second. And it doesn't seem to attenuate, a huge amount, because you're just laying under the water, and you can hear them all. They're all miles away. And then 330 meters per second in air. So that's going to really change things when the echo probe starts to go through lungs. Lungs a little bit faster because it's not just pure air. It's like a sponge, right? So it's a spongy tissue full of air, and 600 meters per second there. So here's a few examples you can go through, looking at the wavelength of the pressure wave versus the frequency, in something like water or soft tissue. So here in this example, we have soft tissue, so muscle, and we're going to calculate the wavelength of sound in muscle, given the fact that we know this is a fixed thing, but we can change the frequency, F, so we can put in 2 megahertz or 10 megahertz or whatever we want. And when we change that frequency, and we do that on the ultrasound machine with a dial, we just click, 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 go to a different frequency, we can change the wavelength of the sound in the tissue. And why would we want a shorter wavelength of the sound? Anybody think why you might want a shorter wavelength? Right, spatial resolution. So if you can make your sound wave more compact and compressed, you should be able to see things that are closer together, right? And we'll see how that works out a little bit later. So this will affect resolution. So the acoustic impedance is, it's related to the speed, etc., and is calculated as the density of the material, right, times the speed of the sound in the material. So now we've got the relationship of the speed, and then whether or not the the material is very dense. This number here can be used, the impedance of a material, well, specifically the impedance of two materials if they're side by side and they're touching, and sound comes through one material and hits the other material. You can use the impedance, the ratio of those two impedances, to determine how much sound goes through that interface and how much is reflected back off the interface, which is a big deal for us if we're imaging. We want to know how much sound gets reflected back, how much sound continues through to reflect off other surfaces in the object, right? So just by common sense or sort of gut feeling, you know, if those two impedances are a lot different, will more sound get transmitted or more sound get reflected if those two materials are really different? Think of slinkies, right? If you had a slinky that was really floppy and one that's really stiff, right? And I take the slinky and I go pa-chung, and I put a wave down through the floppy slinky, right? What happens to the wave when it hits the really stiff slinky? You guys haven't done this either? Man, your childhoods, what were you doing in your childhood? Did you play with slinkies as a child? Yeah, right? So they have a certain, right, index, for how stretchy they are. But if you put that slinky on a wall, for example, and you go pa-ching, the whole wave comes back, right? Right? If it's less stiff, if you connect it to another slinky, that's exactly the same. It just goes straight through, right? So depending on the relationship between the compressibility or the impedance of that slinky versus the next one determines the ratio of the reflected to the transmitted energy. So these numbers are known very well for tissues in terms of, water. Here we are at 1.48. Kidneys a little stiffer. Muscles quite stiff. Bone is very stiff, right? So you're going to get a lot of reflection from bone. And that's why when you're imaging the heart, you must put that transducer between the ribs. You have to shoot the ultrasound between the ribs, right? Because there's muscle between your ribs. Anybody who's eaten pork ribs, right? Yours are basically the same, right? You got the muscle between there. And you shoot the sound through there. If you move it up and it hits the bone, it's all just going to reflect right back at you. Right? Okay, so, and here's a formula for determining the ratio of the reflected intensity over the transmitted intensity using the known impedance of those materials. All right, so I have a sound wave, and it's moving through material 1, hits material 2. This is the amount of energy that's reflected, right, off that interface. And, by the way, I should state that all of this text and explanation and everything is in your folder under week 3, and it's in the Bushberg chapter on ultrasound physics. So if it's confusing, etc., I would advocate you go back and read that chapter to get an alternative explanation or a more deep explanation. Yeah?
So is this the reason it's really important to have that gel between the transducer? Because I imagine between air and...
Exactly. Yeah, absolutely. You don't want any air there. And so as you're moving the transducer around, if it comes loose, then you lose a lot of energy going into the patient. So normally they have this bottle filled with a coupling gel, which is like a really viscous gelatin substance. And they go and just put a whole pile of it on and then put the transducer in that and go through the gel first. Okay, so here's an example using the Z values that are known for fat and muscle. Okay, so we're basically shooting the ultrasound And if somebody has a 1-inch layer of fat on their torso and then it hits muscle, so you're going through the fat, the sound wave's going through the fat, then it hits the muscle, and the question is, how much is reflected and how much gets transmitted. And the intensity of the reflected energy over the incident or transmitted energy is 0.015. So that's pretty small, right? So it tells you that about 1% of the intensity comes back towards you off that boundary. Now remember what our images are. Our images are basically detecting those boundaries and mapping them out. And so the signal from which we're going to make the image of the fat muscle boundary is this 1% of the incident energy. That's what's going to come back to our transducer, and we have to listen for that signal as it comes back. So just like X-rays get attenuated in a medium, ultrasound also loses amplitude as a function of distance in the medium. And this, it's easy to understand that if you're vibrating something, at 10 megahertz, and that wave is going through, you can imagine you're losing energy because you're vibrating the substance and heating it up, right? And so therapeutic ultrasound is when you put the ultrasound transducer on something and you focus all of the ultrasound to a point and you heat the tissue, right? And so that's a little different than imaging. You use much higher amplitudes to do that. You focus all of your ultrasound towards say a 1 cc sphere of tissue, and you try and heat that tissue with the ultrasound. And you can get tissue to, above 45 degrees Celsius, and then that's when tissue starts dying at 45 degrees Celsius, so somewhere up there, 43 even if you hold it long enough. And so you actually cook tissue with the ultrasound. Not in this diagnostic ultrasound level. This is therapeutic ultrasound. So we're orders of magnitude higher amplitudes of energy, and you focus it all at a point. But the point I'm making is that the ultrasound wave itself is depositing energy in the patient as heat, right? And so most of the energy goes as heat. And therefore, as you look at the intensity of the ultrasound wave, as you move deeper and deeper into the patient, it drops away. And it drops away with, the simplest model is this exponential curve as a function of depth. So here's the surface, and assuming we're in the same medium, right? As we go deeper, say 4.5 centimeters into the medium, these curves show you what a 10 megahertz ultrasound wave, how it would attenuate as a function of depth through the medium. That's kind of bad, right? I mean, you look at this. We're down, to 100th or something of our intensity at 2 centimeters into the medium. That's not all bad, because this still can be a relatively high number. You just crank this number up, right? But relatively speaking, as you go down, you lose intensity. Hence, that signal-to-noise drop, as we saw as we moved through the object, right up at the top near the transducer, we had really pretty images of the surface up there, and then as we went down, it got a little noisier. Okay. So this comes into play also in selecting the frequency at which you're going to make an ultrasound picture. Because if we move our transducer to 4 megahertz, we will see objects that are deeper, right? In the, relatively speaking, to the 10 megahertz. And when you're reading about ultrasound and a number of other things as well, because these amplitudes go in a kind of a logarithmic fashion, sort of in factors of 10, as you're moving through the sample, they're often reported in decibels, here, and so here's just for your own, you should know this for just living, the decibel scale, if you haven't already learned it in engineering. But it transforms orders of magnitude amplitudes by a log rate of the ratio, multiplies by 10, so that you don't need decimal points over here. You can just say 60 dB is a factor of 1,000,000, right? And 3 dB is a factor of 2. So it makes the scale really easy to use, right? It's often used for signal to noise, for example, in audio or other things where you have orders of magnitude. So you should know that. So here's an example problem. I encourage you to go through this problem and work it through, and then there's probably other problems in this textbook on this. So the loss, 5 megahertz ultrasound wave traveling round trip to a depth of 4 centimeters in the liver and reflected from an encapsulated air pocket. So they're saying, let's just assume we get 100% reflection at a 4 centimeter depth. Right? And then you ask, well, what's the amplitude if everything goes right? And I put in I naught as my amplitude of the sound wave, and it's reflected 100% at the air pocket. That round trip, what's the amplitude of it when it gets back to my transducer? Because now I have to listen for that echo. Right? So I transmitted it with that transducer. And in ultrasound imaging, you use the same transducer to listen for the reflected signal and use it just like a microphone. Right? So you put it up and listen for sound. And it shows here that the reflection is about 1/100th the amplitude of the transmitted energy. So you're using your ultrasound transducer as your speaker and as your microphone, right? And there's orders of magnitude differences in how the amplitude of vibration that thing has to achieve in order to do that. So technologically, it's an interesting problem, right? In that when you're in transmission mode, you're working like factors of 100 to 1,000 higher than when you switch to receiver mode and listen. So what is this speaker and this microphone? How does it work? Actually, people have made audio speakers out of these piezoelectric, panels and stuff like that. I don't know if anyone's an audiophile, but if you've ever seen those high-frequency speakers that are just flat panels, they're usually piezoelectric crystals, right? And as opposed to a large cone that's attached, that has a coil on it and it's in a magnet, and that makes the cone vibrate. That's how normal speakers work, whereas these guys are just these flat piezoelectric crystals. And the interesting thing about this material is it's a crystal, so the molecules are aligned in a very regular pattern, right? And in their 0 volt, if there's no voltage across here, right, they have a certain geometric alignment, certain angle. Obviously you can cut the crystal to whatever way you want to make that angle. And now if you apply a voltage across the material, because there's obviously a net bias in where the charge is sitting here, if you apply a voltage, you can realign those molecules slightly so they'll all rotate by the same amount. And then the material itself as a piece of crystal will actually shrink, right, or compress. And then you switch the polarity of the voltage, and you take those objects and rotate them the other way, right, and you get a relative expansion around this middle point. And you can do this at very high frequencies, right, so in 20, 40 megahertz, stuff like that. A speaker at 40 megahertz is of no use to you, right, because you can't hear it. Does anybody know how high you can hear? What frequency what's the top frequency you can hear as a human? Nobody knows? It's about 20 kilohertz, right? So when I'm talking to you, da, 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 and the sound waves are coming through here, right? It's all down around probably, a kilohertz, 5 kilohertz, stuff like that. So everything's like wobbling really slowly in your ear, right? Dogs hear higher frequencies, bats hear higher frequencies, things like that, because they have structures that are tuned to those higher frequencies. We do not. And as you get older, actually, your high frequency sensitivity also rolls off, right? And so some people, old people, when you rattle change, right? They don't hear clink, 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 clink really high. They hear like a blurred signal, right? And oftentimes when you're speaking, they mistake what you're saying because they can't distinguish high frequency sounds like S's and T's and D's and these things that require high frequencies, right? Or they just don't care what you're saying. That's a lot of old people, that's where they're at. I'm getting there. Okay, so these are ceramic piezoelectric materials. They've been around for a long time, and ultrasound transducer technology has been being developed over the last 30, 40 years. And so that's, if you get a periodic oscillation of that voltage, you get an oscillation of this geometry, and it produces the vibrations, the sound waves. Okay. So remember what the object that was in the echotech's hand is called the transducer, and this is the front end of the business end of the transducer that's placed on the patient is here, that surface. It's laid down on the patient, and then usually there's electronics that are coming out the back of this thing, which we will see. And here are the piezoelectric crystals themselves, cut to a certain size and geometry, right? And so you have an array of these in order to, and we'll see that the best thing about having an array is you not only increase the field of view over which you can get a sort of a plane wave. If we vary the time that we oscillate these things, we can focus the waves and reorient them and stuff. So let's just take a look at one transducer element. The height of the transducer this way is going to determine our slice thickness, right? The width, or which way is? So this width here is actually the distance of the transducer in this dimension, okay, along the face. And so we have a whole set of them of the same width. And so this will determine, to a certain extent, spatial resolution in the azimuthal direction. And then the thickness of the transducer is just sort of the amplitude that you can vary during the transmission and reception. So a phased array transducer, what happens is each one of these individual crystals is vibrated. They're all vibrated usually at the same frequency, but you can delay, when you start vibrating a crystal, by a few microseconds as a function of position in the transducer array. And then that will create a final sound wave out here that you can customize its shape, right? So you can imagine if we're in La Jolla Shores and you're looking at the water, and I have, like 20 or so very large spheres that I can move up and down, right? If I move those spheres up and down all together, I will get a plane wave that comes in and hits the beach, right? Because the wave front of each one of those things will be the same, and that whole wave will kind of add up and hit the beach. If, on the other hand, I sort of put the ones on the outside down first, and then the ones in the middle a little bit later, the waves from these ones will come in and meet these at a certain point, and so I'll get an accumulation of a wave in the middle of that whole thing, right? And that's what you do with this. You basically, these are programmed delays in the vibration of this crystal. And if I use a minimum delay out here and a maximum delay, because basically the distance to my focal spot is greater out here than it is here, you know, at a specific time, all of those pressure waves will hit this distance simultaneously. And so it focuses the ultrasound wave down to a point. Okay? And so now I've kind of accumulated my energy at a specific focal distance, right? Is there anything else to talk about there? Going back to that original picture, so here's usually the phased array of transducers here. The electronics is coming back here. Again, this is my slice thickness determined by the height of the transducer. The axial resolution is the depth resolution, and the lateral resolution is this resolution. So as my focal point goes down, this lateral resolution gets better, right, at a depth distance. Then it turns out that there's a natural focal distance for the length of this length here, which makes the slice focus at a certain depth below the transducer. Okay. So if we change this thickness, this profile will change. Okay. So in the axial resolution, let's go back. Remember what axial resolution is, this resolution. So can I detect two separate objects that are slightly different distances from the transducer? That's axial resolution. I'm looking down away from the transducer. How close to objects can they be, and I can still call them two objects versus blurring together as one? That's the axial resolution. So here's our transducer. We're just doing this in one dimension, so forgetting about the phased array business. So we have a sound wave coming out. It travels through the medium, and it hits object 1, and then it hits object 2. That causes two echoes to come back, echo 1 and echo 2, and they are some distance apart, both in space and in time. Right? So the space and time are kind of related by the speed of sound and the wavelength. So if I shoot this, which is, it's like a small chirp or burst of ultrasound energy. So it's like a ping, right? Just as in in war movies, when people are in submarines, you always hear like the ping, right? That's echolocation for submarines. And that ping is a sound wave that has a short time, and it goes out, and they look for echoes from objects, right? So this ping, we're gonna take our transducer and go ping, and that makes this burst of energy at our frequency. So this wavelength here is, say, 10 megahertz, right? However, the duration of that 10 megahertz pulse is relatively short. So it's like a burst of 10 megahertz energy, and it will travel through my medium. Right? So as that travels through the medium and hits reflecting surfaces, we get reflections back. And you can see in this case, given the shape of this pulse, right, you know, its width basically produces something about this width, hits this, then hits this. When they come back, they're separable. So I will hear two separate echoes, like a bing bing, as it comes back to my transducer. So I go ping, bing, bing. So now those two echoes I know are different depths. the first echo is the shallow thing. The second echo is the deeper thing. Okay? In ultrasound imaging, right, you saw the detail through that object, right? So we go ping, bing, 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 right? There's like many, many echoes that we're listening to as it comes back to create that detailed picture as depth. Okay? But what we're studying here is how close together can two interfaces be, or two surfaces, such that we can still say they're two surfaces. If they get closer than 1/2 of the width or the length of this ping, then we're in trouble, right? Because the signal goes out, hits this one, starts to reflect, hits this one, starts to reflect, and you get a mixture of the two chirps, right? And so now we've got a summation of those two chirps, and it's going to come back, and whether or not your electronics can figure out that it's two separate things or one is in doubt because they're too close. And so basically your resolution is determined by the width of this ping. So one simple way to make it more narrow, right, is to use the same number of lambdas, so the same number of wavelengths in your ping, but go to a higher frequency. So if I double the frequency, that thing gets shorter by a factor of 2 in space, right? So if here I'm working at 10 megahertz, here I'm working at 20 megahertz, I now have a SPL that's half the size. I can now resolve this thing, right? Because I have two separate signals coming back. So why don't we go to 80 megahertz? About 5 slides ago, there is the major reason we don't go to 80 megahertz. Say it again? It's like that. I can't hear you though. Oh, you could heat up the tissue, that's true. It deposits more energy. And so what happens while it's depositing more energy? Amplitude decays faster, right? So eventually, basically stuff at a certain depth is invisible because all the energy's gone. So that's where this 20 megahertz, 10 megahertz, 30 megahertz, somewhere in there, that optimal has kind of been set because you want a certain depth. If, on the other hand, you were imaging the carotid artery, which is right at the surface here, right? And you don't have to go very far to see the carotid artery, right? And you put that transducer on it. Hell, let's go to 50 megahertz, right? Because now I only have to get in a few millimeters to look at the surface of the artery, right? But if I need to get into the chest and down into the heart, you need to get a depth of what, 10 centimeters, something like that, something reasonable like that. And very high frequency ultrasound for high resolution imaging has been used, right? And for local things, small fields of view. You can actually put an ultrasound transducer on a catheter, stick the darn thing in the body, and just lay it up against stuff, right? And then make a picture of what's right up against the catheter, right? So we're not going to do it in this course. It's not used commonly, but it's a product that's available, which is intravascular ultrasound, where you put a catheter, you got an ultrasound transducer on it, you stick it up in the vessel, and you put that catheter in the artery that has the lesion, and you look at the lesion with ultrasound, like millimeters away from it. You're inside the lesion, right? So make an ultrasound picture. It's pretty cool. Somebody, go ahead.
Why is it 1 over 2? Is it related to like Nyquist frequency, or I don't know? Like, why is
It's probably like, depending on how smart your electronics and algorithm is to separate those two signals, that number would change. Like if you had a really smart algorithm. However, if you just look at the amplitude of, say, 2 Gaussians, right? And you have Gaussian 1, Gaussian 2, and you put them together, such that they're at 1/2, it basically makes one amplitude, right? That's indistinct. It doesn't have two peaks anymore. So that's roughly why it's there. But if you did some kind of interesting phasing of the signal or something like that, you could probably get away with more like that. So this shows the lateral resolution that is available as a function of depth through the object. And here's our phased array transducer. We phase the signal such that there's a focal point right here, right, where the ultrasound comes together at a minimum distance, and then a reflecting sphere, would give you a point spread function across the lateral direction, that's proportional to basically the ability to focus that signal and then do the reverse processing when you hear the echo. And when you image dots, let's say this is a medium and there's little air holes, tiny little air holes in the medium, you get an image that looks like this. You have less lateral resolution very close to the transducer, and then at the focal point you have your maximum, which means it's the smallest in this lateral direction. The full width at half max of that dot goes down to its smallest value here, and then it starts to increase as you go farther away from the focal plane. And the focal plane is adjusted by this transducer, right? By setting the delays on the elements. So if you wanted more resolution up and down here, how could you achieve that? It would take more than one acquisition. There's a hint. Exactly. You just change your phasing, and what I'll do is I'll take my really high frequency focal point and I'll just sweep it down here. So if there's a space over which I want high resolution laterally, I can sweep the focal point. If nothing moves, you can put all those pictures together, right? And say, okay, here's my high frequency image. But the issue with ultrasound is everything's moving. In cardiac ultrasound, everything's moving all the time, right? The transducer is moving because the tech is moving it in their hand, the heart is moving, there's breathing. So you usually deal with it. There are also arrays in which they cut the crystals in the array height direction, and then they'll phase delay as a function of height as well. And that will focus the slice down to a narrower slice at a certain depth, right? So you can basically get an area that you have a relatively better slice than if this was just being vibrated as a native object of that dimension. And so it's called a 1.5D array. I don't know why it's one. It's usually, when I was growing up and all my ultrasound friends were doing ultrasound, they called these 2D arrays. I don't know why this is called 1.5D array, but that's how that works. And then the whole system basically is put together such that there's a transmit receive switch which toggles the system between the transmit mode and the listening mode, and the transmit mode and the listening mode, and you toggle back and forth between those two modes. And then basically you transmit here, and then when it's in receive mode, signal goes through preamps, goes through A to Ds, gets back to the logic of the beam formation so that the inverse can be done on the listening signal, right? So basically I've made a beam this way, and now I hear something back down from the source, so I can put that logic in reverse. And then essentially the time gain, compression, whole bunch of processing on the signals of the individual echoes to make a picture, right? And the picture, you can think of it as if I sweep along this direction in the lateral direction, each brightness is the amount of reflection that occurred at that depth. Right? So let's look at how that echo timing is done. Remember that the pulse width we determined before was determined by the length of time I have here for my chirp, my little ping pulse, and the frequency. Right? So I can make this duration pretty short if I have a high frequency and get a number of vibrations in there. In most systems, we're looking at 1 to 2 microseconds per pulse. Right? So which is, when you're looking at 20 megahertz, is a relatively long period of time. Right? It gives you at least enough for a few oscillations here. In between, so what do? So we have these pings that are coming out of the system, ping, 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 right? Like so. And then when we're not transmitting in this time, we open up the system to receive echo information. So we go ping, listen, ping, listen, right? And this is saying it's about half a millisecond of listening time here, just for this example. So we're going to now look at the time base for just this one period here. Okay, and blow that up onto this axis. So we're going from 0 out to 500 microseconds, or half a millisecond. And ask, what is our depth range that the sound will go down, make an echo, and come back such that we can hear it. And here's the time that we're going, and this is the depth of the reflecting surface that we could achieve while we have that thing open. And so when I do my next ping, basically shut off the listening, and we just ignore what's coming back after that. Anything deeper, right? We'll just ignore it, send out a new ping, right? And look again at the depth down here. So any question about that? So in this example, those pings are coming out at 2,000 per second, and we're listening in that 500 microsecond approximately window after each ping. Okay. So here's the transducer. Electronics connected, and the signal's going back this way, signal for transmits coming in. We make one of these little pings, and it goes down through the patient. This is the patient's chest wall. Okay. This is a depiction of the patient's aorta. So that's the aortic valve here. This is the top of the outflow tract, the left ventricle. And then down here is some basically mitral valve leaflets. This is the mitral valve, and then this whole thing is the left ventricle. Right? So with our transducer here, if we look just along one line, down here we're going to get a reflection from this surface. So this will be the signal that in that 500 microseconds that we're listening, the signal amplitude we measure, if we plot it in time, looks like this, right? Where this is time. So we get a fast echo, 2 quick echoes here, echo, echo, some delay, echo, 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 echo. Right? And so that's the time base of our signal that we're measuring. Is that clear? And so it's like a woo, 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 woo. You hear these echoes coming back. A B-mode image plot of this data is just like we set a threshold for an echo amplitude to say, if my echo amplitude reaches a certain threshold, I'm going to call that a surface, and I'll put a point in my image. And the brightness of that point I can make that is proportional to the height of this echo, or I can just, put a digital point, say, there's an edge there. Usually you make it proportional to the brightness, and that's called a B mode. And so here we have these signals, which are now, instead of a continuous signal here, because this looks perfect. I mean, there's no noise, but you're going to have noise and stuff on here. We actually make this B mode signal, which thresholds that and makes the decision whether or not there's a boundary there. And, how often do I get one of those? This signal here. That's going to change every 500 microseconds, right? So if we go back to this diagram, I do a ping, I measure all those echoes, and I make that B mode plot. Then I do another ping and I get another B mode plot. Then I do another ping and I get another B mode plot. So I get this thing every 500 microseconds. That's pretty good, right? There's 2,000 of those a second. So 2,000 frames a second. I'm measuring where all these surfaces are. Do we need to make images at 2,000 frames a second? Okay, what rate, when you're watching a movie in the cinema, okay, what's the frame rate of the movie? How many times do they change the picture on the screen per second when you're sitting there watching it at your local cinema? How about if I said they change it 1,000 times a second? Does that make sense? That doesn't make any sense, right? Because you can only detect with your eye something around 25 frames a second. Anything above that, like 30, 35, 40 frames a second, it's all stuff that you would not be able to detect the difference. Because your eye-brain visual detector integrates over a certain amount of time, and your baseline sampling rate is somewhere around 30, right? And you can see certain, that the human sampling is discrete, because when you're driving down the highway, if you look at somebody's tire and they have some really nice wheels, with really good spokes on them, say it's a real gangster car that has like 4 of those big spokes, right? And you look at them. When you look, sometimes you see discrete images of the spokes going the wrong way, right? They're going backwards or they're slowly going forwards, right? That shows that your visual system is a discrete sampling system. And the beat frequency of your sampling and the position of those spokes are just kind of landing in phase. So at the perfect rate, you might just see the spokes not changing, right? And then sometimes they move backwards, sometimes they move forward. So we don't need 2,000 images a second. We just don't need that, right? Which is good, right? Because now we're getting data at 2,000 frames a second. So how can you make an image now? We can get this data at 2,000 frames a second. So this is the big aha moment. How do we make a picture out of this? That's like a 2D picture. So I could take this process and just sweep it, right? Sweep it back and forth like a windshield wiper, just going bang, 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 bang. And I can do that such that I can make images at 30 frames a second or whatever, because I'm sampling at such a high frequency, right? So this B mode thing here, I don't have to get it in the same orientation. I can actually move my transducer sensitivity back and forth and make a 2D picture. A 1D picture is trivial in the sense that all I have to do is take this B mode and plot it as a function of time. And I'll get things that look like this. So this echo that comes from this mitral valve shows that it moves it in position with respect to my transducer, as a function of time. Right? And this surface here moves as a function of time, as does this surface right here, which is part of the muscle in the left ventricle, moves as a function of time. When you take these B mode pictures, i.e. you threshold the echoes to get the B mode, then you just plot them in time. That's called an M mode picture. And it's actually still used in ultrasound a lot. Here's a two-dimensional picture of the heart in a short axis. And this is obtained by sweeping back and forth across here, right? Probably sweeping like that, not back and forth. You probably sweep this way, flip around, sweep this way. So each time you sweep across, you measure all those echoes, make a 2D picture, right? What we can look at, what they've done here is they've taken the echo transducer, it's pointed towards the middle of the heart, so you see the left ventricular chamber here. And then they're going to tilt the transducer such that they eventually point in the direction of the valves. There's the aortic valve. So I'm sitting here, point the transducer at the middle of the heart of the left ventricle, then I tilt it until finally I'm pointing up towards the valve plane. Right? And then what you can measure, actually simultaneous of doing this imaging, this is the M mode plot of the central line through this image, right? And so you see the left ventricular contraction. This chamber changes its dimension as a function of time. It gets smaller here, then it opens up when you have diastole or filling. This is the EKG, the blue signal down here. So that's the ventricular signal here, and then the distance between this white signal right here and this signal right here is the wall thickness, the myocardial wall thickness as a function of time. So this is the diastolic wall thickness here, end systolic here. Okay. And then as we start to see, papillary muscles, they are echoes that are inside the chamber that change as a function of time with each heartbeat. And then here are valve planes that are also changing as a function of time with each beat. So that's M mode scanning. That's what this is called. It's great for measuring very precisely with super high time resolution certain things like myocardial wall thickness or whether or not a valve is moving at the right speed. And then this is the 2D image by sweeping that beam across the patient or the field of view. And so this is how you do the sweeping. Okay. So we have a phased array of these crystals, and we used the phased array in this condition when we were looking at it the first time to focus the ultrasound energy such that it was at a narrow point or a focal point optically, right? And we can then adjust the phase of these to take that structure and point it to the left or point it to the right. Right? And so that we'll sweep back and forth to make that set of 2D pictures. Okay? And so this is the transmit timing delay required to do those sweepings. Okay, so we have 10 more minutes. This is a really cool thing about ultrasound is the fact that if the object that you are bouncing or reflecting the ultrasound from is moving, it will actually shift the frequency of the ultrasound. So if I have a surface here and my transducer's here, I send out a ping at 20 megahertz, and my surface is static, stationary. I get a reflection. When I deconvolve that thing, it's at 20 megahertz. On the other hand, if this surface is moving away with a velocity v, I ping at 20 megahertz, I hit the object that's moving away from me, and then receive my ultrasound signal back. It will be 20 megahertz minus an amount that is proportional, linearly proportional to that velocity. And if the surface is coming towards me, I ping, coming towards me, the frequency upshifts, so I get a higher frequency received. So looking at the shift in the frequency, which is a pretty simple thing to do electronically, it's been done forever, you can measure the relative velocity at the instant that that echo occurred, right? That's pretty powerful, right? Because a lot of stuff's moving around, you would like to know how fast it's moving, right? And interestingly, even though when you make images, you kind of ignore the blood signal, as we saw here, right? This is blood in here. The signal's way down in the noise, so you don't really look at it that much. However, when you start looking at velocities, yeah, actually you'd like to measure the blood signal because that's the velocity you're interested in, say blood in the aorta, whether or not blood is going through a valve at the appropriate speed. So you actually start looking at the signal down in the blood, and this still works, obviously, because you have, in fact, little reflectors, little ultrasound reflectors in the blood, which are like blood cells, erythrocytes, and things like that, actually reflect blood. If you want to reflect a lot of signal from the blood, you can inject bubbles, little micro bubbles, tiny little air bubbles into the blood, and then such that they're so small they don't hurt you physiologically, but they are hugely echogenic, right? They make this big reflection of echo. And so when you're measuring blood velocity, so if you have your vessel oriented this way, say we're measuring, we've got our transducer this way and we're trying to measure the velocity in the aorta, it may not be perfectly aligned with the transducer. I mean, it may not be coming straight at the transducer. So if the blood's going this way, we send out a ping and it gets reflected back this way, then you have to take into account the geometry of the flow with respect to the direction of the ultrasound in order to get the velocity estimate right. But it's a simple correction, right? It just goes as the cos of the angle that between the line of sight of the transducer and the vessel, right? So as theta goes to 0, you get a very simple formula that the change in frequency is linearly proportional to the velocity itself divided by c, etc. So this is the frequency incident. This is the frequency detected. So if the velocity over c is positive, you get a frequency upshift. And this cos theta term just appears as the geometry goes around that vessel. That's pretty simple. This is used a lot in echo. It can't be understated how important this is for detecting certain things in cardiovascular disease. One thing that you really want to detect is whether or not a valve actually is stopping the blood when it should be. Right? You can sometimes hear that, but it's very difficult to understand just how badly the valve is damaged or not working just from sound. You'd really like to see what's the velocity of blood going the wrong way through that valve. And so this is a mitral valve. This is the left ventricle. Top of the left ventricle is the aortic outflow tract. The blood should all go out here. The mitral valve should shut when the ventricle contracts. And in this case, you can see all of the velocity is going up through the aorta. So we're measuring velocity as a function of direction away from the transducer. So you see there's a peak velocity here. This is all going away from the transducer. This is coming towards the transducer. And then in diastole, when the ventricle is filling with blood, the velocity is coming towards the transducer. Okay, that's the red color. So they have this color here. So blue is away, red and yellow is towards the transducer, and that's what we see here. And so that's normal function. That looks pretty good. And then maybe next week we'll look at some abnormal jets. So if this was abnormal, there would be a signal here, right, on this side of the mitral valve, and what color would that signal be? It will be the same as this. It will be traveling away from the transducer in the wrong direction, right? And then you can measure basically the velocity of the jet.